These notes cover some of the basic functions we'll be covering in Algebra 2 over the course of the year. So we call them parent functions because they're going to be the simplest version of these functions. So first up is the parent linear function. So parent linear function is just f of x is equal to x. So this would be a line with a slope of 1 and a y-intercept of 0. So you can see on the graph over here, we have a slope of 1, and the y-intercept is right here at 0. If we fill out a table of values for this function, the f of x values are always just going to match the values for x. So if x is negative 2, then f of x would be negative 2. And if x was negative 1, negative 1. And x can be any number. If x was 0, we'd get 0. If x was 1/4, we'd get 1/4. Positive 1, right. So when we talk about the domain of a continuous function, what we're saying is these are all of the values for x that I can put into this function. So for something like the parent linear function, the domain would be any number. You can pick any real number. So the domain of this function would be all real numbers. And usually we'll write the shorthand for that. Remember, we learned from those sets of numbers, you can specify the set of all real numbers by writing this fancy looking R, right? So that stands for all real numbers. And the range of this function is also all real numbers. And when we say range, that's the set of all possible y values. So domain is all possible inputs, and the range is all possible outputs. But obviously the range can also be any real number. So on to the next one. This is the quadratic function that you've probably seen before. There's a common mistake when people refer to this function. So the name of the function is a quadratic function. The shape it makes is a parabola. So it's just more of a nitpicky thing. The shape it makes is a parabola, but its name is a quadratic function. So the equation for this is f of x is equal to x squared. So if we fill out a table for this, if x was negative 2, then negative 2 times negative 2 is positive 4. If x was negative 1, we would get positive 1, 0, 0. If x was 1, we'd get 1. And if x was 2, we would get 4. So the domain of this function, once again, we'll ask ourselves, is there any number that exists that cannot be squared? And the answer to that is no. So the domain of this function would be all real numbers. The range, however, so we're talking about all the outputs here. And one thing you notice here is this graph, it's never going to go below y is equal to 0, right? Because if you square a negative number, you get a positive. Square a positive number, you get a positive. So the range is going to be all real numbers greater than or equal to 0. So 0 would be the absolute minimum value of the range, and then anything greater than that. So in shorthand, because in math we always like to write things with the fewest number of pen strokes possible, we would just say y is greater than or equal to 0. So below we have the square root function, which is the inverse function of the quadratic function. Inverse function is a vocabulary we'll expand more on later. But this is just saying you take a number x, and instead of squaring it, you now square root it. So you can kind of see the graph here, it looks like a half of a parabola that got turned on its side, right? And in fact, if you continued it this way, you would end up with an entire parabola. But if we continued it down this way, then it would no longer be a function, right? Each x value would have two y values. So the square root function refers to only the positive square root of a number. So if we fill out a table of values over here, if x was, say we picked x was -1, then the y value would be undefined. Undefined. Because the square root of -1 is not a real number. It exists, but not in the real numbers. Now, if x was 0, the square root of 0 is 0. If x was 1, the square root of 1 is 1. Now, if I pick, so I'm going to pick 2 next. Well, if I pick 2 next, the square root of 2 is an ugly irrational number, so I'm going to jump up to 4. If x was 4, the square root of 4 is 2. And then if x was 9, then the square root of 9 is 3. So the domain of this function, so notice when we sub in -1 for x, we get an undefined y value. What that's saying is that -1 is not in the domain of this function. And in fact, we know that the square root of any negative number is not going to be a real number. So the domain of this function is going to be any real number that is greater than or equal to 0. And similarly, the range, since our x values are restricted to be positive x values, then that also is going to restrict our range to only be positive y values. Because if you take the square root of any positive number, you get a positive number. And like I said, those of you that are thinking, well, doesn't a number have 2 square roots? Yes, but this function implies only the positive square root. So if we wanted the negatives, we would put a negative in front, because otherwise it wouldn't be a function. And this is specifically the square root function. On to the exponential function. So the exponential function is when you have the variable as an exponent. So this is any number, almost any number can be raised to the power of x, but it specifies b has to be any real number that is greater than 0 and not equal to 1. Again, we could write b is greater than 0 and b is not equal to 1. Now, b is not a variable. It's still going to be a constant, but the exponential function family really has a large number of bases you could put as the base of the exponent. So the graph on the left here is 2 to the power of x, and the table will fill out on the right that we're actually going to start on the bottom for reasons you'll see in a second. So if x is 2, then 2 to the second power is 4. In fact, I'm going to add one box down here. If x was 3, then 2 to the third power is 2 times 2 times 2, so that gives us 8. And we know anything raised to the power of 1 is itself, so 2 to the first power is 2. Now here's where people start getting lost sometimes. If x is 0, 2 to the power of 0 is 1. The reason for that is, so notice if we're going down in the table, when we go down, then what we do is multiply the previous number by 2, right? So to get from 2 to 4, we do times 2, and that gives us 4. Times 2 again, so here we did times 2, and then from 4 to 8 is another times 2. So if we're going backwards in the table, then it makes sense that we would be dividing by 2. So to get from 8 to 4, we do 8 divided by 2, and that gives us 4. 4 divided by 2 is 2. And then 2 divided by 2 is 1. And if we keep going backwards, so if x was -1, well, 1 divided by 2 is a half. And if we go even farther backwards, a half divided by 2 is 1/4. So when you have negative exponents, really you're taking reciprocals and then raising the positive part. So 2 to the power of -2 is the same as 1 divided by 2 squared, which is 4. So if we look over here, the domain of this function, and any parent exponential function, regardless of what the base is, as long as it meets these requirements, the domain of that function would be any real number, because any number can be an exponent. So here we can see negative numbers work as exponents, and we'll learn later that you can also have fractional exponents. The range of this function, so notice when we go farther down in this table, we're going to keep dividing by 2. But no matter how many times we divide by 2, we'll never hit 0. So that means the range of this function is any real number strictly greater than 0. And in fact, here at, so the x-axis on this graph is what's called an asymptote. So the exponential function has an asymptote. At y is equal to 0. And an asymptote, again, it's something we'll cover more later in the class, but I wanted to bring it up now. 1, because it's relevant, and 2, because I just like saying the word asymptote. But an asymptote is a line that a graph approaches. Line that a graph approaches. And usually we refer to asymptotes at like extreme y values. So no matter how many times, no matter how far we go to the left, if we keep going, the graph will never touch the line y equals 0. So now that we've learned what an asymptote is, look at the asymptotes on this mother function. Here we have this is called the reciprocal function or the rational function because it's a ratio, right? And this is 1 divided by x. So if we go over here to the table, if x was -1, then 1 divided by -1 is -1. If x was -1/2, 1 divided by -1/2 would be -2. But what happens when x is 0? Well, like I keep bringing up in class, this is saying you have 1 cookie divided among 0 people. And that doesn't make sense. You can't divide 1 cookie among 0 people. Like it's not that it's 0, because saying that it's 0 implies that there's someone there not receiving a cookie. This is undefined. Undefined. If you were looking at the table on your calculator, it would probably say for error. So, and then if x was 2, we would get 1/2. If x was 3, we would get 1/3. But because it's undefined here when x is 0, that's what that tells us is the domain of this function is all real numbers except 0. Any other number you can have as the denominator of a fraction except 0. So in shorthand, because that's how we like it in math, we would just say x is not equal to 0. And in fact, it has an asymptote at x equals 0. You'll never reach that line. And just like the exponential function, it also has an asymptote at y equals 0. Because no matter what number you put as the denominator of a fraction, 1 divided by any positive or negative real number is still going to be something that's not 0. So we have also an asymptote that y is equal to 0. Which means the range of this function is any real number except for 0. The y value does never equal 0. The absolute value function, which we looked at a little bit, we looked at the absolute value operation earlier in this class. So here you're taking a number and you're taking the absolute value. So if x was negative 2, then the function would equal 2. Negative 1, we get 1. Because absolute value is how far away the number is from 0. 0, 0, 1, 1, 2, 2. So notice it has symmetry. For any negative x, the absolute value is just the positive. And for any positive x, the absolute value is the same number. So the domain of the absolute value function is all real numbers. And the range of the absolute value function, well, we said the absolute value can never be negative. So it has a minimum at 0. So it's anything greater than or equal to 0. So this is the cubic function. So this is x raised to the third power. So if we fill out the table here, so when we cube a negative number, so negative 2 to the third power, so think when we square it, it's positive again. So negative 2 times negative 2 is positive 4. But if we multiply by negative 2 again, then we're back to a negative number, and we'd have negative 8. So negative numbers raised to the third power stay negative. So negative 1 to the third power is negative 1. Of course, 0 to the third power is 0, 1, 1, and 2, 8, right? So you can see on the graph here, it's going to go down forever and still to the left. So that means, and it's going to go up forever and to the right. So the domain is going to be all real numbers. Or you could just think, is there a number that can't be cubed? No, you can cube any number. So the domain has to be all real numbers. And the range, so again, I brought up that it goes down forever and up forever. So that tells us that the range is also all real numbers. Because negative numbers can also be, since when you cube a negative number, you get another negative number. Eventually it passes through all of the real numbers. And the last example for today is the cube root function, which is the inverse of the cubic function. So cube root is to cubing something as a square root is to squaring something. So notice there's a 3 sitting on the radical there. That's a 3. So that's saying what number raised to the third power is equal to x. So if I say I start here down at 8, what number raised to the third power is going to give me 8? And that's going to be 2, right? 2 raised to the third power is 8, so that means the cube root of 8 is 2. And if I had 1 here, it would be 1 again. Say I had negative 8. So unlike the square root, the cube root is defined for negative numbers. Because if we look back up here for a second, when you cube a negative number, you still get a negative. So that means if you take the cube root of a negative number, you still have an answer, right? So the cube root of negative 8 would be negative 2. And say the cube root of negative 27 is the next perfect cube. That would be negative 3. And these go a little bit out of order. Say I had the cube root of 1/8. Well, what number raised to the third power would give me 1/8? And you can really just look at the denominator, and you know that it has to be 1/2. So you multiply a half by a half is a fourth, and then multiply by a half again, and you get 1/8. So just like the cubic function, the domain and the range are both going to be all real numbers. So this is just a brief overview of all the functions, most of the functions we'll talk about in depth in this class. So yeah, that'll be it.